Welcome to lesson 8.7, special right triangles. So the main idea as we go through today's lesson are there are two types of special right triangles. One that we call a 45-45-90, also called an isosceles right triangle because two of the sides and angles are the same. And then we have a 30-60-90. And what we're keeping in mind as we go through this lesson is that the side lengths of these special triangles relate in a rather simple way. So there's a general rule for finding these side lengths. So the first one we're going to look at is the isosceles right triangle theorem, also known as the 45-45-90 triangle theorem. Same exact thing. So isosceles right triangles are 45-45-90s. What we mean by that, the 45-45-90 name comes from the angle measures. In an isosceles right triangle, two angles would be 45 degrees. Obviously, one has to be 90 for it to be a right triangle. So that theorem says, in an isosceles right triangle, if a leg has length x, and remember our legs are the two sides that meet at 90 degrees. So if our legs have a length x, the hypotenuse always has a length of x multiplied by the square root of 2. So if we know a side length is, let's say, 3, our hypotenuse then is 3 multiplied by the square root of 2. So let's use that in example 1. I apologize for the sign piece here. You can just cross that off. That shouldn't be there. But let's look at part A. We have triangle ABC here, and we know side AB, a leg, is 6.4. So side AC here also has to be 6.4. Both legs are the same. Our hypotenuse, which I labeled Y, would be our leg, 6.4 multiplied by the square root of 2. So we can simply write that as 6.4 square roots of 2, or if you put it into your calculator and round it to the nearest hundredth, we should have 9.05. In part B, they gave us the hypotenuse, GH, which was 10 units. So I know my two legs, GI and HI, are the same. So if I label one X and one Y, they're the exact same. So to find a leg, I'm going to work this rule from this theorem backward. So if the hypotenuse is a leg multiplied by the square root of 2, to get back to the legs, I need to take my hypotenuse, 10, and divide it by the square root of 2. But if we go back to Algebra 1, we know there's a mathematical rule that says we cannot have a square root in the denominator. No radicals in the denominator. So how do we simplify that? So 10 divided by square root of 2, to simplify, we multiply the top and bottom by that radical on the bottom. So both get multiplied by square root of 2. So then we have 10 square root of 2, and on bottom, square root of 2 times square root of 2 is just 2. Can simplify the 10 and the 2, and we would have 5 square root of 2 for our answer. So both of our legs are 5 square roots of 2, and if we wanted to get a decimal answer, that's approximately 7.07. Now example 2 is taking this theorem and putting it into a word scenario. So it says the bottom step of the Mosley's pool needs to be replaced. The cost of the repair is based on the size of the step. The side view of the step is shown at the right. FABD is a trapezoid with AB being parallel to FD and FD perpendicular to DB. The Mosleys know that AB equals BD, AD equals 12 inches, and FD equals 18 inches. Round the area of the side of the step to the nearest square inch. So first off, we know, looking at our diagram here, the step, FD was 18 inches, AD was 12, and then we have this 45, 45, 90 triangle to finish off the step. So I'm first just going to pull out that triangle. So I know it has a hypotenuse of 12 and my two side lengths, which are AB and BD. So if I wanted to find one of those, I'm using my theorem and working it backward. So I'm going to divide by the square root of 2. So x would be 12 divided by a square root of 2. Need to simplify again, so we multiply top and bottom by the denominator, which would be square root of 2. And then we have 12 square roots of 2 over 2, which simplifies to 6 square roots of 2. So we know that side AB and side BD are each 6 square roots of 2. Now what I can do is look at this trapezoid overall and break it into its two triangles. If I look first at triangle FAD, or AFD, however you want to label it, triangle AFD's area would be 1/2 the base times the height. My base is the 18 inches. The height would be from segment BD here, which would be 6 square roots of 2. So the area of triangle FAD would be 1/2 times 18 times 6 square roots of 2. So the triangle AFD has an area of 54 square root 2 inches squared. I just left it as a radical rather than changing it to a decimal right now. Then I need to figure out the area of this little right triangle ABD. So that's again half a base times height, and my base and height are the two legs. So base is 6 square roots of 2, height is 6 square roots of 2. So 1/2 is 6 square roots of 2 times 6 square roots of 2 is 36 inches squared. So then to figure out that whole area of the step, it would be the area of that trapezoid FABD. So I'd take my two triangles, 54 square roots of 2 plus 36, which gives us approximately 112 square inches. Then we get to our other type of special right triangle, our 30, 60, 90. So obviously another theorem to go with that, the 30, 60, 90 triangle theorem. In a 30, 60, 90 special right triangle, if the length of the shorter leg is x, then the length of the longer leg is x multiplied by square root of 3, and the length of the hypotenuse is 2 times x. So if we draw an image of that, triangle ABC here, if angle A is 30 degrees, side BC would be my shorter leg, opposite that. So BC would simply be x. AC is my longer leg, so that is whatever the shorter leg is, x, multiplied by square root of 3. And AB is my hypotenuse, so that would be 2 multiplied by my shorter leg of x. So there is our rule, our theorem for special right triangles in an image. So we have our shorter leg, multiply that by square root of 3 to get the longer leg, and then to get the hypotenuse, it's 2 multiplied by the shorter leg. So let's look at example 3. It says find the missing side lengths of triangle BIG. So in triangle BIG, I know G is 30 degrees, so B has to be 60. Side IG is 9, and that means IG is my longer leg, because if I think about it, the shorter leg's the side opposite 30 degrees. So IG is the longer leg, which is 9. We need to find our shorter leg and our hypotenuse. So I'm going to start with BI, the shorter leg. So to find BI, it's going to be our longer leg divided by the square root of 3. So we'd have 9 divided by square roots of 3, which we need to simplify. So top and bottom each get multiplied by the square root of 3. So we end up with 9 square roots of 3 over 3, which then would simplify to 3 square roots of 3. So segment BI, my shorter leg, is 3 square roots of 3. Now we need to find BG, the hypotenuse. Well, now that we have the shorter leg, that's really easy because the hypotenuse is simply 2 multiplied by the shorter leg. So 2 times 3 square roots of 3 simply gives us 6 square root of 3 for side BG's length. So again, for 30, 60, 90, use this theorem here. For 45, 45, 90, use the isosceles right triangle theorem or the 45, 45, 90 triangle theorem. Same exact thing. Then we get into our last idea for this lesson. So based on those special right triangles, we have a regular polygon area formula. So remember, a regular polygon means that all the sides are congruent, and then all of our angles would also end up being congruent measures. And it has to be convex. So a regular polygon, all the sides are the same length. So the area of a regular polygon is half the product of the length of its apothem, which we'll get to in a second, and we represent that with a lowercase a, because area is an uppercase a, and its perimeter, which is represented from a lowercase p. So first, let's just look at perimeter. Perimeter on any regular polygon is the number of sides multiplied by the side length. So if I had 5 sides, the perimeter would be 5s. If I had 20 sides, it would be 20s. The apothem of any regular polygon is the segment joining the center of the polygon to the midpoint of any side. So I drew 2 examples up here. So if I have a regular pentagon here, take the center point, connect it to the midpoint of any side, and that length is the apothem. Or if I have an octagon over here, center point to the midpoint of any side, and then that length of that segment is the apothem. So the regular polygon area formula would tell me if I had a regular pentagon, it'd be 1/2 multiplied by the length of that apothem multiplied by the perimeter, which would be 5s. Or if I'm dealing with a regular octagon, it'd be 1/2 multiplied by the apothem multiplied by the perimeter, which would simply be 8 times the side length. So example 4 is asking us to use that rule right here, a equals 1/2 AP, but we first need to figure out the perimeter and area of this hexagon. So all they told us is that the hexagon had a side length of 10. But that's all we need to know to technically draw a regular hexagon. So image is already provided for you. We have our hexagon HIJKLM here, and we know our side length is 10. So then if we drew in the apothem would be this segment from our center O down to P. And we can break that into looking like this triangle here. So I'm going to pull that triangle out for a second. So I know the apothem is the distance of OP. So if I look at triangle KPO, just this triangle here on the left, I know it's a 30, 60, 90 triangle. If I knew this whole distance down here was 10, I know K to P is 5 and P to J is 5. So my shorter leg of triangle KPO is 5. The apothem, OP, is my longer leg. So using my 30, 60, 90 triangle rule, I can find that distance of my apothem, OP, by taking my shorter leg and multiplying it by square root of 3. So OP, the apothem, is 5 square roots of 3. Then the perimeter of this hexagon. Well, hexagons have 6 sides. It's regular. So our perimeter would just be 6 multiplied by the side length of 10. So our perimeter is 60 units. Now that allows us to find the area of that whole hexagon. So the area of HIJKLM would be 1/2 AP. So 1/2 multiplied by 60 multiplied by 5 square roots of 3. So in other words, 30 multiplied by 5 square roots of 3 is 150 square root of 3 units squared. And again, we could take, if they wanted a decimal answer, the 150 multiplied by square root of 3, and then round that to however many decimal places they need. The 150 square root of 3 here is left in its radical form, but it is the most accurate because we didn't do any rounding with decimals. So really our lesson comes down to 3 main ideas. The regular polygon area formula. Area is 1/2 the apothem times perimeter. Our 30, 60, 90 triangle theorem. Shorter leg is x, longer leg is x squared root of 3. Hypotenuse is 2 times the shorter leg of x. And then our isosceles triangle theorem, or isosceles right triangle theorem, or 45, 45, 90, where if our legs are the measure x, the hypotenuse is x times the square root of 2.